Hi, I'm Florian and I'm here to tell you about our paper Scalability and Precision by combining expressive type systems and deductive verification. This paper is based on my master's thesis and it was written together with my advisors Alexander, Matthias and Vano. So, pluggable type systems can be used to obtain formal correctness guarantees by extending a language's existing type system without much specification overhead. For Java, for example, we have the checker framework. If we take a look at this program, we want the first parameter to never be null, whereas the second parameter and the local variable can be null. And in the checker framework, we can express this by introducing these type qualifiers non-null and nullable, and then we can use the checker framework to obtain the formal correctness guarantee that this program never throws a null pointer exception. And while this approach works and scales very well with large programs, there are also false positives. For example, the statement highlighted in red here will be marked by the checker framework as possibly causing a null pointer exception. But if we take a look at the upper half of this function, we can see that it sets the variable br null to a non-null value if and only if AR null isn't equal to null. Therefore, this if clause here ensures that AR null can't actually be null at this location. So this is a false positive. What can we do to avoid this? An alternative to pluggable type systems like the ones from the checker framework is deductive verification. We can use the Java modeling language, JML, and some deductive verification tool like Key or OpenJML. Here in this listing, I've replaced the type qualifiers from the checker framework by JML specifications, and with this we could use some deductive verification tool to prove that these specifications always hold. This of course has fewer false positives than the checker framework, but it scales very badly and it leads to a large specification and verification overhead, because these tools are much harder to use than some pluggable type system from the checker framework. So we asked ourselves if it wasn't possible to combine the advantages of both type checkers and deductive verification. So this is the core idea behind our contribution. We wanted to combine the scalability of type checkers with the precision of deductive verification. Our pipeline starts with a program which is annotated with some property types. These property types consist of some base type, like object, some type qualifier, like the ones we just saw, non-null and nullable, and in addition, a Boolean expression which expresses the semantics of the type qualifier. So for the qualifier non-null, this would be something like this subject is not equal to null. We developed a type checker called the property checker, which can be instantiated with any arbitrary property type hierarchy and checks the well-typedness of the program. Any parts of the program whose correctness the property checker can't prove are translated into JML assertions, while any parts it can prove are translated into assumptions. And this JML translation is then proven in a JML deductive verification system like Key or OpenJML. So our contribution can be summarized in one of two ways, which are really just two sides of the same coin. Either we use the deductive verification to strengthen the type checking and to avoid false positives, or we use the type systems to make deductive verification easier and less time consuming. So going back to the start of our pipeline, what are property types? I just said property types consist of a base type, like A in this example, a qualifier, like non-null, and a Boolean expression. They are defined in a domain-specific language like this, and this definition can be given to the property checker in addition to, this definition can be given to the property checker. But in addition to this, to just defining the property qualifiers themselves, we also have to define the hierarchy between them. In our example, this is pretty simple because non-null is obviously a subqualifier of nullable. But for the sake of example, let's add another qualifier to this hierarchy with the property that not only the subject, the typed variable, isn't equal to null, but also its fields aren't equal to null. Now, if we take a look at just the type properties, then we can see that deeply non-null could be considered a subqualifier of non-null because its property implies the property of non-null. And a deductive verification tool would be able to see this and tell us that deeply non-null is a subqualifier of non-null. However, the property checker can't argue like this because it doesn't look at the properties themselves. Instead, it only looks at the hierarchy which we explicitly give it. So we have to explicitly tell the property checker that non-null is a subqualifier of nullable and that deeply non-null is a subqualifier of non-null. Because otherwise the property checker doesn't see any relation between those qualifiers. So using this hierarchy, the property checker checks the program and any statements in the program whose type correctness follows from this hierarchy are discharged, while any statements whose correctness doesn't follow from this hierarchy are translated into JML assertions. If we go back to our example, then the statement marked in green can be proven by the property checker because the variable a is declared as having the type non-null a, whereas the statement marked in red can't be proven by the property checker because the variable a or null is declared as having the type nullable a. So if we translate both of these statements into JML, we get these two assertions here. And because the green assertion has already been discharged by the property checker because it follows from the type hierarchy, the translator turns this assertion into an assumption. Whereas the red assertion is left as an assertion. The reason why we turn the things which have already been discharged by the checker into assumptions instead of just removing them outright is because these additional assumptions sometimes help the deductive verification tool in finding a proof. Now in the last stage of our pipeline, this translated program is given to a deductive verifier like key or OpenJML. And in our example, this translation suffices for those tools to be able to find a proof and proving this program to be correct. In some cases, depending on the complexity of the proof obligations, we may actually need to add some additional JML specifications, but not in this example. To evaluate our approach, we used two things. First of all, we took the Daikon invariant generator, which is a pretty big Java program which uses the checker framework. And we just looked at some code snippets where there were false positives caused by the checker framework. And we made those snippets self-contained, simplified them a bit, and tried to discharge these false positives. Here in this example, you can see that there's a suppress warnings annotation because the checker framework can't tell that the variable slice is always non-null at this point. But using our approach, we were able to translate all of the type annotations into JML specifications and discharge this false positive. The second part of the evaluation is a small case study where we wrote a small Java program and annotated it with some type qualifiers. And then we first tried to verify the correctness of this program using key. When you translate all of the type qualifiers in our case study to JML, this leads to 117 assertions, which Key has to prove, and Key is able to prove these in around 500 seconds. Now, if we let the property checker run before translating everything to JML, then the property checker is able to discharge 90 of these assertions by itself, leaving only 27 for Key to prove. And this leads to a much shorter runtime of around 300 seconds, so 311 seconds for Key and 8 seconds for the property checker. The reason there's an asterisk here is because we intentionally designed the case study such that the parts which are easy to prove, which can be proven by the property checker alone, are separated from the parts which can only be proven by Key. So we had some parts of the program which were completely verified by the property checker and which we didn't even need to load into Key. And this is what led to this big runtime advantage. If you have a program where the difficult to prove parts aren't cleanly separated from the easy to prove parts, then you won't really see such a big runtime advantage, but you may still see a decrease in specification overhead. Because the additional assumptions added by the property checker actually did help Key find some proofs. As you can see on this slide, in the version where we didn't use the property checker, we required 55 additional JML clauses in addition to all of the property types to prove the program's correctness. But in the version where we did use the property checker, we required only 50. So in addition to a decrease in verification overhead, there was also a decrease in specification overhead. To conclude, we implemented a property checker which checks the correctness of a program based on some simple type hierarchy, which can be instantiated with any arbitrary type hierarchy. We also implemented a JML translator which translates those parts of the program which the checker couldn't prove into JML assertions and the parts it could prove into JML assumptions. And this JML translator works for both main JML dialects, which are Key and OpenJML. Now, for a short outlook, what would we like to improve? First of all, the property checker which we implemented is possibly the weakest type checker you can imagine, because it has to support any arbitrary type hierarchy with which it is instantiated. So we'd really like to make our approach work with stronger type checkers. We'd also like to implement better support for dependent types, because currently the property checker just ignores those completely and translates them into JML for Key to deal with. And we'd also like to support mutability, because one restriction, which I haven't mentioned yet, is that we restrict ourselves to immutable types, which is of course not really good for an imperative language like Java. So we are working on support for mutability at the moment. And that's it from me. Thank you for your attention, and here you can find the most important links to our paper and to the property checker.